All right. Good morning. Let's start. Last time we talked about ensemble EMD, and this class we're going to present a few more examples, and then we'll have a conclusion of this. The first example that I will give you is a geophysical data. This geophysical data consists of surface temperature data from two different. We have already talked about this. Yeah, we talked about this already. Let's see. We'll talk about another set of geophysical data. This geophysical data is SOI. We have seen SOI before. SOI is actually the Southern Oscillation Index. It's the pressure difference between Port Gabon and Tahiti. Yeah. And the other one is sea surface temperature at El Nino 3-4. El Nino is such an important geophysical phenomenon. So people start to measure surface temperature as an indicator for the El Nino event. In the Nino 3-4, it's one region around the equator near the western Pacific. Yeah. So they measure the temperature, the whole area of temperature and the average. And if you look at the data, there are two sets of data. The blue one is the surface temperature, and the red one is the pressure difference. Yeah. You look at this, it seems to be that they are totally random. But if I present a small section of this from 1970 to 2000, you will see that this data has a very interesting interplay. That is, when the surface temperature increases, the pressure difference decreases, and when this pressure difference increases, the surface temperature decreases. So they are opposite. They are almost exact opposite. This is because that the theory is that the Southern Ocean oscillates, and that is either the consequence or the cause of the surface temperature increase. Yeah. So in geophysics, the geophysics is very, very complicated, and exactly how this is come around, it's still not totally known. Yeah. For example, whether El Nino is caused by the autonomous oscillation or it's caused by wind shifting is again something which we are not totally understand yet. Nevertheless, the observed effect shows that they are almost 180 degrees out of phase. One is plus, the other one is minus. Now for this data, many people study geophysics. Is okay, if EMD has such powerful consequence, why don't we apply this method to this set of data? When you apply this set of data, you get a surprise. The surprise is that the anti-correlation, the 180 degree out of phase effect, it's not clear at all. See, over here we already have very bad mode mixing, and over here we may see some phase locking, but in other place we don't see that at all. And if you see other components, the other components are almost totally random. And as a result, when EMD was first introduced, many people tried to use it, but few people get a total success because of the mixture of the scales. And if you project this into the time frequency domain, you can still see the frequency, where the frequency resides, whether they are annual cycle or a multi-annual cycle. That's clear. But that is a more blurred picture. the clear picture is to actually look at the face. And the face information here is totally lost. Yeah. And this will have to wait until that we have ensemble EMD. You look at all these components. Most of the components actually has very bad phase relationship. Now we will try to add some noise to it. And once you add the noise, this here we use 0.4 standard deviation of 0.4. Standard deviation 0.4, and when you enlarge, this adding, whether you add this noise or not add noise, doesn't make any difference after you average it. And now you look at the component. The mode mixing totally disappears. Yeah. Here, in order to make the comparison better, we have flipped the sign so that it will be in phase. So this in phase area, see all the area, almost every one shows in phase in step data component. And when you look at the down, that's very nice. But this component has serious problem. This component is very interesting. This component, at the beginning after you flip the face, it's very nice. But the later part, the early part of this, from 1860 all the way to 1940, the behavior is very, very different as compared to the later part. In nonlinear system, there a lot of time the system has more than one state of equilibrium. In other words, for example, we use a pendulum. The pendulum can be swinging this way, and the swing as the swing amplitude increase, and it will actually rotate around the origin. So that it becomes another state. Yeah, and in other area, so you may have more than one attractor, and you may oscillate here and then a jump oscillator over there. That's very often. So whether this is a totally switch of state or not, people realize that the state actually changed. Yeah, and that is also show up in this data. Now we have added 0.4, 0.4 RMS. Here we have 0, 0.1, 0.2, 0.4, all different, again, with different level of RMS. But all this is trying to demonstrate that if you add the RMS, the noise, at a different magnitude, it really does not going to change your result drastically. What will change your result is that once you add more noise, you need more average to get the better result. So the only one that is not, this is again surface temperature. The only one that is not with data added is the blue one. So the blue one immediately stand out, showing us as a mode mixing result. The first component here, it's almost totally noise. And if we keep on looking, and again we see that the one that really does not agree with all the group is actually the blue one. Yeah. And this is a CTI, it's the surface temperature. And again, see the blue one becomes a singular point. And here is the SOI. SOI is much better because the SOI, the surface temperature differences already is very noisy to begin with. So it has noise all over the place. But the surface temperature is not. Surface temperature has intermittency. Because surface temperature will average over an area. Sometimes it's very smooth, sometimes it's not. So this SOI is, the change is small, but nevertheless it's still there. Now, I want you to concentrate in the bottom panel. The bottom panel plot the correlation of 0 noise added and the 0.4 noise added. The 0.4 noise is added is the blue one. The 0 noise added is the original data, is the red one. So when we're here, we're plotting the correlation coefficient of each component. Now we can see that the first couple of components, the correlation is 0. That means it's all noise. Noise should have 0 correlation. So we don't have any correlation. And as we get a longer scale, we see that in the component number 3, we have a negative correlation of around 0.3. That is an anti-correlate. The correlation is negative. That means that one data is positive, the other data is negative. Yeah. So we have 0.3. And then to the fourth component, we get a point near 0.5, but not quite, 0.45, and then a 0.25 and 0.2. So overall, you don't see a clear anti-correlation between the two data, because nothing is beyond 0.5. They are all below 0.5. It's negative, all right, but it's not very clear. Once we add the noise to be, we add the noise of 0.4 RMS, we can immediately see number 1, number 2 components are still uncorrelated. Yeah. But once you get to 0.3, the anti-correlation increased to almost 0.5. It's already better than this one, than the best one. And then when you come to 0.4 and 0.5, it actually goes to almost 0.75 or 0.8 negative correlate. So the anti-correlation at this particular scale are very clear. Now recall, when we demonstrate white noise and we demonstrate the significance, we use SOI data. The SOI data, number 1, number 2, component number 1, number 2, are practically noise. So we don't pay too much attention. Actually, the ones that are above and beyond 95 percentile or 99 percentile signal are actually 4, 5, 6, 7. Yeah. Now, 4, 5, 6, 7, they are all highly anti-correlated. Yeah. Except number 6. Number 6 is clear. The scale is clear. It's clear the signal. But the phase is not. The phase has a shift. Okay, so this is an interesting geophysical phenomenon that the number 6 is not exactly like over here you have a highly anti-correlation. Yeah. So with this, then we know that the Southern Oscillation Index and SCI are indeed anti-correlated. And which component are anti-correlated? The component anti-correlated are concentrated here. Not all the data are anti-correlated. So this gives us dynamics, which shows that beyond annual cycle, almost to decadal, it's much better. The dynamics actually occur over there. Now, so straightforward seems to produce low correlation IMF from 2 different time series. And then the correlation tests indicate that the ensemble EMG can separate time scale and in the IMF. So they can improve the correlation significantly. By improving the correlation, we mean that we actually see the dynamic consequences of those components at those particular scale. And if we apply this to sound, I have used this example repeatedly. This is when I say hello. Yeah. But if I say hello, this hello, even though hello is a very simple sound, but they are, which is consonant, and low is vowel. Most of the sound actually is from the vowel, not from. Yeah. When we talk, about 20% is in consonant, 60% is in vowel. Another 20% is in pause. So between words, we have to pause. Otherwise, it will be continuous. It's very hard for us to listen. But when you sing song, it's different. When you sing song, people sing. It's 90% vowel. Yeah. But what is the purpose of vowel? Vowel is to make the consonant continuous. Yeah. So when we sing song, we always add a lot of vowel sound at the end, especially in Chinese song. We put R, we put E at the end, so to make the sound continuous. And that is why opera is mostly seen in Italy, Italian. And Italian has a lot of vowel ending words, so they can continuous. And because 90% are vowel, another thing is that a vowel does not convey information, unfortunately. Yeah. If you write up any sentence, you block up all the consonants. You only see the vowel. You will never make sense of it, because there are very limited number of vowels. Yeah. If for any sentence like hello, if you like this, if you take D away, T away, H away, L away, you get the A, E, O. Can be anything. Yeah. Book, take the B and K away, the O. It can be look, can be book, can be anything. Yeah. However, if you take away the vowel and leave the consonant, it still makes sense. Yeah. Like the delta, take the D away, T away, DT. Perhaps delta. Yeah. Book, BK. it almost makes sense. Because of that, there are languages has no vowel. Yeah, only consonant. That language is the very, very old language, probably one of the oldest language. That's Hebrew. Yeah. Hebrew has only consonant, has no vowel. And if you want to read it, you have to provide the vowel yourself. That was not a problem before, but it's increasingly becoming a problem, because after Israel becomes independent, many Jews from different areas moved back to Israel, and they developed a special dialect, 像我们的方言一样 dialect, yeah, and so they can provide different vowels in that. So when they read out, it's a little bit different. So as a result, recently they have started to develop a few symbols to help you how to pronounce the word. Yeah. So Hebrew is very, very old language among the present existing language. I believe it's probably, other than Chinese, or it's probably the oldest language in the Indo-European area. What happened is that, of course, original language was developed by Egyptians and by the Mesopotamia. That's the Iraqi people. They have cuneiform, and the Egyptian has hieroglyphic. And then the Phoenician copied it to get the alphabet. Yeah, and then Hebrew copied them, and then Greek copied them. When Greek copied them, Greek put vowels in it. Yeah, alpha. Yeah, so those are then the Rome copy of Greek. So and the rest of the language follows. So the phonetic language none of the phonetic language are original language. They are all borrowed. Yeah. So when you look at this is a big vowel sound. So when you sing song, especially in Chinese song, I have difficulty understand what the singer is singing. None of the songs I understand, because 90% becomes vowel. 90% does not convey information. Only 5% is consonant, and you have pause too. So it's very difficult to listen to sound for me. That is, some of the people have better trained ears, And so when you're in a choir, everybody sing together, a good choir will have one group only pronounce the consonant. So instead of singing the whole song, it just yeah. So when people hear, they hear clear consonant sounds. Yeah. But anyway, so this is when I say hello. Yeah, it's very clear it's hello. I'm fortunate I cannot play this, otherwise you would hear. Now this hello, when I use EMD, this is what I got. I was very proud when I got this because I was able to separate the sound and separate the sound into different frequency components. And if you look at it very carefully, you see I do have a problem. The reason is that look at this component. This component is of one frequency, and this frequency and that frequency and that frequency does not mix with each other. And this frequency, however, mix with that. And whenever you have that, I have a low frequency. So if I can move this up, if I can move that up, and then move all this intermittently up, I would get a continuous signal. But I cannot. Okay. At the time that I got this result, I comfort myself and say, oh, no problem. When I project it back in time frequency domain, it will appear okay. Sure, it appears acceptable. At least it appears better than all the other methods. The kind of detail that it reveals is much more interesting than others. But the problem that we do have this mode mixing still stands. Like this one, for example, this frequency and that frequency obviously doesn't belong. But if I put this frequency and that frequency together, and this frequency and that frequency together, then I would get a very nice component. Yeah. So for this example, if we use EEMD, what we got? We got it. We have all the components coded together. See, this frequency is from beginning to end, yeah, and this frequency is no longer fragmented like this. This should move up, this should be moved up, and so on and so forth. Yeah. So with EEMD, indeed we got this. And once you get that, and I will jump forward, this is time frequency. Time frequency, the low frequency is so continuous, and all the frequencies are very nicely located. And if we do not use EMD, we'll see that even if it projected back from here, suddenly jump down. But this jump down, it inevitably left some gaps. Yeah. So the artificially induced transition will cause the frequency, in frequency time space, the signal is not continuous. Yeah. So by using EMD, we gain a lot of advantage. We can drastically improve the decomposition. And if you look at the detail, look at how continuous this is, and look at how discontinuous this is. Yeah. And so for this, we are already better than the wavelengths, and better than Fourier. But we can only say we give you more detail, but it cannot tell me what the detail means. Yeah. Does this mean nonlinear, or does this really that my voice is vibrating like I was putting up a special skill trying to make my voice vibrating? No, it's vibrating is caused by data analysis methods. Yeah, but if you use this, then it's very clear. Yeah, it's continuous until here. My voice is a little bit nonlinear, and the frequency is oscillating up and down. In the reverberation, after I say hello, and then the sound is vibrating in my vocal chamber. Yeah, and that's not linear. Yeah. So So these are very clear. So what we got from all this? What we got from all this is summarized here. The true IMF can be derived from adding finite amplitude noise. But this is very important. Previously, people had add noise, like by the British group, they add very small noise. They claim that the true noise, the true signal is noise-free signal. Yeah, that's very intuitively correct. But it turns out it's not true, because the true signal should be a many trial. You should explore the neighborhood of the correct answer. How can you explore the neighborhood? You add a noise. You try to perturbate, you try to push it away, you see whether it come back. Okay, so try to push it away by adding noise. Once you add noise, then it perturbated, but you have many different perturbations. You put it together, it actually gives you the correct answer. And noise has to be of finite amplitude. You cannot just place, well, I add a 0.001. Yeah. Nevertheless, I have to report to you, there are places you would like to add a very small noise. That's a different use, but that's not a use to get actual component. See? So we have to add a finite amplitude rather than the case with infinitesimal noise. And the ensemble indeed enable us to separate scales of separate components with a different scale. Here, we no longer need a priori criteria of intermediacy. Yeah. And that makes the method still totally adaptive. Yeah. And the method, see, the beauty of the method is adaptive. But once we've added intermittency, it's no longer adaptive. But here, I have to again to say that when you try to solve a problem, you don't want to make a stand based on principle alone. You say, okay, I'm be adaptive, therefore if it's not adaptive, I'm not going to use it. That may not be the best approach. When we do research, the best is the best result, not the best methodology or whatever. Okay. So in applying this method, we do not have to stick to a principle that I have to use EFD or whatever. You can still use intermittency. For why? You know what you're doing. How can you know what you're doing? You can cheat. We can cheat a little bit. Yeah. The way to cheat is that you first solve the problem with wavelet or with Fourier or whatever. You find that indeed there are certain frequencies. Then you can set your intermittency at that particular frequency. You may still get a very good result. Okay, and sometimes I still use that method because later we'll tell you I will repeat this point later because EEMD still has certain method, certain drawbacks, shortcomings. Yeah, and the shortcoming is what? Is this. The sum of IMFs may not be an IMF. I have an IMF. I have another IMF. IMF add IMF is not an IMF. So in other words, the set is not closed. For example, I have sine A, which is IMF. I have sine B, is an IMF. Sine A plus sine B may not be an IMF. Yeah, you can add a sine, you can add a high frequency sine. The high frequency sine is IMF. Right? When I add, then I get bumps everywhere. Yeah. So, therefore, this immediately has an impact on the approach. That if you add noise, you get IMF. You say this is first ensemble. Add another noise, you get another ensemble. Each one is IMF. But if I add all the IMF, do I get an IMF? Not necessarily. Yeah. If you're lucky, yes. If you're not lucky, you perhaps will not get an IMF. But the scale is all right. Look at all the other examples. the scale are separated very nicely. What do I mean by not IMF? By not IMF means there are reasons I'll cover. So, as the components produced by EMD are the average values of the IMF, so they may not be IMF. Some of the components may be has multi-extrema. So one way may skew this way, the other way may skew that way. When you add, then you have double hump. Now, so that is a problem. Now, how can we be sure that we always get a good IMF? We don't know yet. I don't know yet, but I will show you some of the study that I'm trying to explore this. This EMD, ensemble EMD, is a wonderful tool. It's a great discovery. It's a big improvement over EMD, but there are problems that we are still exploring. Now, how can you improve this IMF? As an example, I use a noise. This noise is 1,000 points, white noise, a general white noise. Then I will use ensemble EMD to decompose it. The ensemble EMD to decompose this, I will decompose to get this component. This is ensemble, I warn you. I'm not just doing once, I'm doing, in this case, I think I did it 30 times. I should go back and look. Yeah. So this is when I use stoppage criteria, s equal to 1. Yeah. Then if I use s equal to 10, I will get a different set. In other words, once I use different stoppage criteria, I would get a slightly different component. So I get different components like this. Now let's see. If I look at the enlarged, the first component, I look at a particular section. This section, actually, I just grabbed the section out of IMF 1. Yeah. What I got, look at this. This is not the IMF. This is not the IMF. Many locations, the result, the mean, is not IMF anymore. It's no longer IMF. Yeah. And if I look at the average 10, I get much less problem. The problem is alleviated. It's reduced. So I tried different. I tried different stoppage criteria, and I also tried different noise. I tried to get a better result. Oops, so in this case, I tried different. I tried a different way. Okay, I tried a different way. Here, what I tried here is I tried a different noise level. See, we have already demonstrated that noise level doesn't matter. Noise level doesn't matter if we have enough ensemble number. See, if you fix the ensemble number, the noise level does matter. Yeah. So when you use noise level, then you will see that as the noise level increases, the orthogonality index getting worse. In other words, the noise level will start to creep in. Yeah. And yeah. So these are the two trials of the different noises. So the result is about the same. And if I use the stoppage criteria, the stoppage criteria 1, 2, 3, 4, 5, And as I increase the stoppage criteria, I will have a trend of decreasing the orthogonal indexes. So, in other words, if I put more stringent stoppage criteria, I would get a better result from this. So, armed with this, then I becomes more more intrigued. So I decided to ask a colleague of mine to do a complete program, to do a very dense study of here is the stoppage criteria, and here is the noise level. So there are two variables. Then I can check the orthogonal index. And this is the concept he got. And to this day, I just get this last week. We're still discussing. This is very, very new. I'm still discussing with him. I don't think this result is reasonable. But I still show it to you. That is, we have here a noise level and the stop criteria and the orthogonal index. Yeah. The orthogonal index has a trend of leveling. And the first trend is clear. That is, if noise level is low, the orthogonal index is good. The noise level is high, the orthogonal index is not very good. But if I give the given noise level, if I keep on increasing the stoppage criteria, make it more stringent, and this curve shows an opposite trend. So you increase the criteria, it actually gets worse orthogonal index. Yeah, that's something which I don't quite understand. There are many possibilities. The one possibility is that I was wrong. The other possibility is that he was wrong. Of course, he may be wrong because his program may have a problem. Okay. Now let's look at this. This is again a fixed number of shifting. That means let's use this. The fixed number of shifting of power 2. This is a shifting twice. I stop. A shifting. This is shifting 2 to the 2's power. That's shifting 4 times. This is shifting 8 times, 16 times, and so on and so forth. Yeah. Each component has a fixed shifting time. Yeah. This is the stoppage criteria advocated by Dr. Wu. Yeah. And if you look at that, again, the trend for noise is reasonable. The trend for shifting, more strengthened shifting, actually make the case even worse. Okay. Now here, as I said, I have problem, and because I have problem, you have problem too. Because I cannot make that very clear. I want to make it clear, so I will assign this as a homework. And you go back and do your study of noise level and shifting criteria to see which direction that you got. Okay, so you will be, we are in the same boat. We know the same amount of information, either right for it or wrong for it. Okay, but to do that, I will add one more. For the homework, I will add one more. This one more is this. I'm not sure orthogonal index is a good criteria here. Yeah. Why orthogonal index should be good? That's something I don't know. Now, you can see that in the notes that I sent you, it's not there because as I'm teaching, I'm thinking too. so this is reflect what I thought last night or maybe this morning even. I think the orthogonal index may not be a good criteria because see, EMD always separate the scale out. And if the scale is not the same, then the orthogonal index will be pretty good because a different scale makes dot index, dot product, the inner product types always. But the problem that we have is not that the EMD, whether the EMD can separate the skill better, clear. Our problem is that whether EMD, the result of EMD, produced single extrema between 0 and crossing. So a better criteria should be this, and that is the excessive extrema. So what you should do, instead of use orthogonality as a criteria, you try to count the extrema with 0 crossings. So the criteria should be 0 cross the extrema number minus 0 crossing number normalized by 0 crossing number. So how many percent of the wave has multi-extrema? Yeah. For each component, you add it all together as a measure of that particular component. Okay. Let's plot a oops. Let's plot a surface contour using EE index. Yeah. If we use EE index, then we will find out how many EMD actually is bad. Yeah. So this will be a better criteria. For those who sign up for the course, this is assignment. Okay. I will not have final examination, but if you do not hand in the assignment, I cannot give you a grade. All right. So make sure that you hand in the assignment before the end of the semester, whichever the semester is. In Japan, you can sign in by email. Here you can sign in by email too. Please give all the assignment back to the our teaching assistant here. Okay, and he will collect it and I will read it, and then give out your grade. So this is an assignment. Here again, I have to discuss the fixed shift number gives a better orthogonal index. That's what from our trial. But as I said, orthogonality may not be a good criteria. So I will not vouch for this statement. It indeed gives me better index. However, if you select the fixed shift number, if you select the shift number very low, like 10 times or whatever, that's fine. If you select very high shift number, the computation is very expensive. You're going to keep on, especially when you go to the lower and lower number, you just keep on doing that. You don't have to do that, but you still have to, since you set that as criteria. So this is a very, very time consuming. And not only that, then you will have to choose, as the program is written, you have to choose the number of IMFs. How many numbers? Sometimes you choose 5, maybe you come out with 6, and so on and so forth. Those are problems. But those are the problem, the defects built in the present method. You don't have any other alternatives. Again, I will repeat this. Not all EMD produced components are IMF for 2 reasons. One is the sum of IMF may not be IMF. The other one possibility is leakage. The leakage is this. So if I use noise, I can produce this scale, like the third component is this, the fourth component is this. In between this area, it can be either 3 or 4. So those are the leakage of the filters. Both these reasons could cause problem for us. Yeah. So what we have to do is we have to try, and by trying this, we find that it's not bad. Yeah, the result is not bad. but it's how good are they? It's what we really want to look into. Now, once we get this, even without the leakage, without the components, not IMF, reconstruction is not a problem. In other words, you add all the components, you get back to the original data. That's always true because the methodology dictates by algebraic equation. The sum of the components always is the original data. So the completeness is always true. What is not true is that the energy may not conserve. In other words, if it's not orthogonal, the square of the data may not be equal to the square of all the components. And that's where the problem comes in. So to guarantee that, we do need a rectification. Yeah, we want to get rid of this excessive extrema. If you have more extrema, you may have problem. The problem is that in between zero crossing, you have multi-extrema. When you do Hilbert transformation, that may not give you all positive number of instantaneous frequency. Yeah. So when you compute the frequency, you have to rectify in order to get the meaningful instantaneous frequency. Yeah. So since we are doing time frequency spectral representation, oh, thank you very much. Since we are doing time frequency analysis, we may want to do rectification. The rectification in the past we've done is after we get the signal, and we do another EMD to sort out this. And that is not a perfect, clean operation, and we still have some problem. Yeah. So EMD is the big advancement, but they are still unresolved problem. And so that's why this class or this course is a part of the course is a progress report. So we are still moving toward a better solution. Yeah. Another observation, it's again a very, very late development. When we add noise, we add noise number one, we add noise number two. And actually two persons suggest. The first one suggests to me was a friend of mine in the United States. 3 years ago, he came to me. He says, "Hey, Norton, when you add noise, why don't you add noise, one copy of noise, and then add noise times -1. In other words, add a positive noise and a negative noise. So the 100 noise, instead of add 100 noise, you add 50 noise. Half of that is positive and half of it negative. And because the positive and negative will cancel out exactly, so your end reconstruction may be much cleaner. Well, I thought that's nice, but I also thought it may be a problem because I want the average to be totally independent. If I have the noise, positive noise, negative, and they are exactly 180 degree out of phase, whether that will help me or not, I was not sure. Over the phone, I told him, I said, please try. And this guy, this friend of mine, is very, very smart. But unfortunately, he is intellectually, I would not say lazy, but not very proactive. Yeah. So after he discussed with me over the phone, he says, okay, I'll think about it. So 2 years later, I asked him, have you done anything? He said, no. And 3 years later, I asked him, have you done anything? No. Until last year, here in Taiwan, a graduate student at Yuanzhi University, yeah, he was doing heartbeat. And he just did it. Yeah, without even thinking, he just did it. And when I asked him, why you do it? And he said, well, I thought it would be better. Yeah, but indeed, it is better. So this, because his PhD dissertation defense is next week. So this is very, very new. I debated for a long time whether to share this with you, and I say, sure, I will share with you. But this is the case is that when you implement noise, you implement in pair. One with plus sign, the other with minus sign. Yeah. And that will actually, the pairwise add could reduce noise in the final reconstruction. So this is a very, very late development. I don't know whether, perhaps you may have already published it, I doubt. Yeah. So here's our conclusion. The conclusion is that ensemble EMD method to be truly dyadic. Yeah. By truly dyadic is that each component is indeed, the scale is double, twice. Now, if you do not use that, the problem is that you may not be totally dyadic because of the mode mixing problem. So, this to be dyadic, you have to use EEMD, ensemble EMD. By adding finite noise, the ensemble EMD totally eliminated the mode mixing problem. Yeah. And the problem generated, that's a different separate issue. Ensemble EMD used the scale separation principle of EMD to represent a major improvement. I still, even with the problem that I mentioned, I still think it's a major improvement in the EMD. So if anybody wants to read more about this, please read the full paper. The full paper is in the first issue of Advances in Adaptive Data Analysis. Yeah, and that is you can free download that paper. Either go to the web by typing Advances in Adaptive Data Analysis, or go to our NCU web Research Center for Adaptive Data Analysis. You can download those papers. Yeah. And if you do not want to download, you can come to my office. I can give you a hard copy. Yeah, I do have a reprint. Therefore, with this observation, we think the true IMF component should be the result of the ensemble EMD. The ensemble EMD from the raw data. Yeah. The sum of this is not necessarily IMF. Therefore, ensemble EMD may not be IMF. That is one thing that we have to be very, very careful. Yeah. However, you may ask, how come that the hello signal is so well, you produce the frequency so well? If it's not IMF, how can you produce it so well? It turns out that the Hilbert transformation sometimes is also pretty forgiving. For small violation, it does not show up. You may hide a lot of things in the mathematics and computation. When we come to the Hilbert transformation, we'll discuss that. So, that's the conclusion. EEMD is equivalent to the artificial ensemble mean of EMD. Okay. When we go out and do an experiment, each experiment will have its noise. So we do ensemble. Why we do ensemble? Because we don't trust just one trial. The one trial may have a particular noise, so we try many, many trials. But in our data analysis, we are provided with just one data. We don't have the ensemble. So what do? We artificially create noise to change this one set of data to be everywhere. Yeah. But in this trial, indeed we get something very nice. But there is, however, perhaps I should write that down. One thing we cannot overcome, that is the original noise in the data. Yeah. The original noise in the data, EEMD treat that as the data, as if it were part of the data. There's no amount of noise addition you can get rid of the original noise in it. So in a way, I thought this is something like our original theme. You will never get rid of that. that is in the data itself. To get rid of that, you have to have genuine ensemble. In other words, you observe it once, observe it twice, observe it three more times. Unfortunately, that's not available most of the cases. Yeah. So we use this EEMD to be an artificial ensemble. The artificial ensemble is still incomplete. Okay? But it's improved. So that will be the ensemble EMD. All right. We're going to move to the next topic. So we're moving gradually. We'll talk about all these things related to ensemble and spreading. When I did the earthquake result, I find a very annoying property of EMP. That is the spreading of the data into the quiescent region. If you have the data like this, and if you use EMD, what you do is that you have this, because you have a long space, has all 0 points, and it's very hard for you to determine what is the extrema and the 0 point. So you get this, you get that. See, this a very ugly thing. It's look like an effect. It may not be n, but in this particular case, it is n. And if you use E, ensemble EMD, you don't have that. Why? Because I have to add noise in it already. So adding noise can actually help you keep the straight part straight. Yeah. But another way to you compare this. See, this is just EMD. This EMD, you have very poor orthogonal index, and if you use ensemble EMD, you get very nice until you get here. Here, it's not too bad because the wave numbers become so long. You may only have a couple waves together. Overall, the ensemble, the total, all the off-diagonal components, this is very, very poor. 49% leakage. Yeah. Here, we only have 6%. Okay. So ensemble EMD indeed help. So this end spreading is an annoying problem for something that before the sensor turn on, you already get signal. That's nonsense. Yeah. So the EMD has a tendency to spread it. The end spread causes deterioration of this EEMD, solve the problem to a large extent. Yeah. The noise add. The EEMD alleviated this end spreading problem considerably. There are still cases the signal need to be contained. Yeah, we want to contain it. For example, EMD is add finite amplitude thing, and in the EMD2 we add small infinitesimal. Yeah, infinitesimal actually has advantage too. So, for example, this delta function, and we can perform EEMD, and we will get a ensemble, and that looks good. Zeros now. Here, I want to make a point. I only make 10 trials. If you make 100 trials or 1,000 trials, and this will be very good. You will get a very symmetric. All the data will be like the symmetric thing. But if you're not doing enough, the ensemble may not give you good enough answer, especially when you come down to lower and lower components, because those components, the amplitude becomes smaller and the noise becomes more prominent. So spread the signal is to make the noise spread away. The delta function originally is at one point. Now we get to spread it away because of the either use ensemble EMD or whatever. it always spread away. So what we can try. The ensemble EMG has another problem, is that because the noise is generated, each time noise is generated, totally independent. Okay, so I can try one time, I generate a set of noise. Try another time, I generate another set of noise. The influence of noise will only disappear when the number of ensemble approach infinity. Yeah, then all the average add out, they disappear. Yeah, they all add up to zero, average out. But if you do not do enough, this is your problem. Here is 10 times. I tried it one time, I get this. I try the second time, I get this. These two are not identical. Yeah. So not enough ensemble will cause you problem. Yeah. So this is the third trial. You get still a third different answer. So.
Excuse me,
yes.
Professor Fang.
Yes.
Hello. The camera does not working, so
oh,
I can't see anything.
Yeah, I'm sorry. By the way, you only get the picture from the camera. Is there any? Do you?
I just see the blue screen.
We saw the same thing. We saw a little bit better. We saw a very noisy screen.
Oh, okay, I can see that. Thank you.
No. Yeah, but do you have the notes that I sent out? I posted on the web.
Yes, we have.
You have.
So I can. Yeah, we can see that.
Yeah, you can see that. Without the screen, that may be the only thing you can follow. My colleague is trying very, very hard to try to fix the problem. Today, I'm sorry, today is the a special event because our regular office, regular classroom was used by what, a engineering show or something. In the engineering side, they have a material show. Yeah, they have a conference going on. They need that need that classroom. So we got to put in this fancier classroom. But unfortunately, the telecommunication here is not up to par compared to that classroom. Let's try. Let's take a break. Let the colleague try to fix it. If they cannot fix it, maybe to be fair to you, we'll just stop. And then we'll start next week. It's only half hour. I only cheat half hour, okay? 怎么样？我先去过去，他现在是测试嘛？休息。那有没有办法？
没有，直接换教室。
啊？
直接换教室。
不，再换教室，哎。
可是可能修不好。
不，修不好我知道。我想我们还是民主方说，投票大家都说不要上课。我这个人很信民主啊，我现在是开始秀汗，我是换教室还是不要上课？我下课就过去了嘛。啊，换一个教室，我想we have had 25 minutes, right? And after the commotion, it's not worth the time. I think. Hello, our fellow students. We now are conducting a democratic process here, and we'll show a hand, see whether we want to dismiss the class. And from their laughter, I submit that we all want to get off early. This is not their fault. This is a technical fault. Okay, so we will come back next week. Because a blank screen is not very conducive to learning. All right. I'm sorry. I'm sorry for this technical
problem.
difficulty. Okay, you have a nice day.
Yeah, thank you
enjoy.
very much.
You enjoy.
Yeah, thank you.
25 minutes free time.
Yeah, thank you very much.
All right, bye-bye.
It's very fun.
Sayonara.
Okay, fine. See you. Bye.
See you next time.
See you.
喂，那台大听得到吗？就下课了。喂，好。
下课了，我们先下课了啊。Class dismissed。
台大有听到吗？没有。
你看我这个 decision obvious 是 very popular 啊，没有人生气的。这个 is a reflection of my skill as an instructor。只要是好的 instructor 说我不上课了，大家都心里不高兴。Okay, see you next week. 你们 by the way 你们有问题可以问 before we leave， 有没有问题？我们不给他们听，我们自己可以。
那个 leakage 这个问题是 always happen 还是说普上这个
leakage 是 always happen， 这个是 probability， yeah。但是呢 ，if you do enough average 啊，它的主体还是不 leak。有的东西会 leak， 但是在那个 main part 是不 leak， 所以它这是一个 problem。但是我们做的所有的 problem 啊，我们都发现它 result is very nice， 所以这个不是一个主要的问题，但是它是一个问题。
尤其在上很多 IMF 时候会严重起来。
上
就是 EMD 的 ，EMD 的。
EMD 里面会，但是 EMD 你知道，我没有，我不去。你记得这个 spectrum 这样画，我们画的是真正的那个 main energy 那个 part 还是没有 ，mix 的都是那个 tail end，tail end 的它的 energy 非常少，不是非常要紧，但是它是一个 power。OK， 你 average 多的时候，它那个变成更不重要，因为每一次都是那个 peak 的地方比较紧绷。好。
因为老师那个，好像刚才讲的永远没有办法考虑去弄 noise 它量。那个原因是因为你的 noise 是 zero random。
No. We cannot get rid of the original noise because original noise is part of the signal. It appears every time. It's not random anything. It's deterministic. So you add on, it's there. It's add on, it's there. It's add on, it's there. So it's always there. So you cannot average it out. The original noise. So I think that in a way 像我们那个基督教讲的 Christian the original sin you cannot get rid of it. It's going to be with you all the time.
最后一个，
对。
德拉方程，那个德拉方程，我本来以为以前就 EMD 可以，因为 EMD 不能做德拉方程的 composition， 念 EMD。那我们以前以为说，它做出好多个 IMF， 然后越来越开得很漂亮。可是今天听老师的课，我发现那反而是不正确的。
不正确的。
德拉方程它应该就是第一个 IMF 有，其他不应该有啊。不然以为说，后面越来越开，那个很漂亮，而且后来今天发现它不是。
Delta function is very local. Only at that point. Any method made it spread, it's not local. Okay. So far we find that none of the method I know can be extremely local like that. Okay. So what I'm going to discuss here is a method I think it may make it more local. Okay, EMD is going to let it spread. Let it spread dionically. The first time is 1, the second is 2, and then 4, and 8, and 16, and so it's spread out.
So that may be a problem of small problem.
Well, it is a problem of any method. It's a problem, like, for example, what method is the most unlocal is Fourier. Fourier immediately spread everywhere. The sine, cosine is everywhere. So Fourier, if you use delta function as Fourier, 1,000 points gives you 500 sine sine wave from beginning to end. There's no local area at all. Okay. Spectrograph is local because you have windows. Okay. Wavelet has its own spreading. So none of the other methods can be strictly local. EMD is the same. EMD and ensemble EMD, they are all equivalent to a dielectric filter. A dielectric filter is also equivalent to a dielectric wavelet. So it has Patrick Swanson proved this dielectric wavelet. How he proved that? You just look at the shape, compare the shape with the dielectric wavelet, the same. Yeah. So it's spread just like a wavelet. Yeah. But the advantage that we have over the wavelet is that our shape is adaptive. Yeah. Our method is adaptive. And being adaptive, then we don't need the kind of harmonics that's required for a priori determined basis. That's the advantage. As far as spreading is concerned, no method can strictly control it. What I'm going to introduce next is a way. It's a very awkward way, but nevertheless, it might work better. What I did is to add infinitesimal noise, but add infinitesimal noise every time. Every step you add a noise. You see, the reason it's spread is that if you add a noise at the beginning, as it goes down, the scale of noise starts to spread. But if you do it once, and you take away a component, and you take the difference with the data to get a residual, add another noise. And this noise is a small scale again. So the spread is the maximum real scale. Each time is the original scale. So in that way, it may be combined. Okay?
Yeah, that's the details about adding noise. The first time we have original data, so we can count the standard deviation, and we say that 0.4 of the standard deviation become the noise amplitude and add it into original data. Then we got first component and then the residual. Should we count again?
No. In ensemble EMD, you add noise. One noise goes through the whole procedure. That's one ensemble. Take the data again and add another noise, another ensemble. Each ensemble add noise only at the beginning, no more. After you add noise, it goes through the whole thing. And because you have a consistent noise going through the whole thing, so by averaging it, it will cancel out. If you keep changing it, it may not work because you add a different noise. So that's why in the other way, because we keep on adding new noise at each step. I will explain that later. So you cannot use different noise. If you use different noise, it's not going to cancel out. Okay. Any more questions? 好，下次再见。
那同学有一个是 mail 写给我是 NTSNAIT 的是哪一位？没有这位哈，没有人来，没有来。
在这里选课的同学啊 ，make sure 你要把那个 homework 交上去啊。我希望你们这个 homework 在12月中以前交。那在我们12月底以前呢，我们还可以有一个 discussion 啊 class。我们课上到12月底，1月就考试了，是吧？12月中以前把 homework 交来 ，OK， 我们可以 discuss。我发现。